Starting the last day of the event, the plenary speaker will be Professor Rachida El-Assoudi from INSA in Rouen, in France. And she will be talking about semigroups generating simple Lie groups and optimal control. Okay, Professor Rachida, you can start.
Thank you for the presentation. I like to thank the organizers for this very interesting event. I also thanks for the invitation, and sorry for my English is not very good. I will speak slowly. So I will give in this presentation necessary and sufficient condition for semigroup S to be equal to the whole group. So I will begin by some noun property about root system of simple Lie algebra, and I will present a Cartan decomposition related to an arbitrary root, and I will recall some property of Lie saturated cone. I will give all the results concerning this problem. And after, I will speak about Subramanian geometry and control optimal on Lie group. So, consider a semigroup S of a simple Lie group G, which is infinitesimally generated by a subset gamma of the Lie algebra of G. The problem when the semigroup is equal to group interested many others, and different approaches are used to resolve this problem: homogeneous space, flag manifold, and algebraic fact. Here, I will use just algebraic fact, and it's based on property of a root system. So I recall some known property of a root system of simple Lie algebras. So we take G of finite dimensional complex simple Lie algebra, H of Cartan subalgebra of G, and R the set of roots associated to the pair G and H. We have a root space decomposition of the Lie algebra given by this. The direct sum between the Cartan subalgebra and all the line G alpha corresponding to a root alpha. The root subspace is defined as here. We know that if we have alpha is a root, minus alpha is also root, and every root subspace is of one dimension, and we have this Lie bracket property. Also, the root system is a subset of the dual of the Cartan subalgebra, and for any root there exists unique vector A alpha and M1 alpha satisfying this Lie bracket, and the Killing form between A alpha and A minus alpha is equal to 1. We choose an element H alpha in the Cartan subalgebra such that alpha H alpha is equal to 2. So I will use the Cartan integer beta H alpha defined as follows. These integers take these values The non-degenerate symmetric bilinear form on the dual of the Cartan subalgebra is defined by with this relation with the killing form. For in a route there exists a reflection R alpha defined as well, and this reflection lets stable the set of a route R alpha beta belongs to R. The Weyl group is just the group generated by of all this reflection R alpha route, and the Weyl group act transitively on the set of a route. So this action give two orbits corresponding to short route and long route. So the classification of simple Lie algebra use the Jenkins diagram. Jenkins diagram is just a connected graph with the vertices are simple routes, and the number of the edge between two simple routes is equal to the product of this number of Cartan integers. These products take the value 0, 1, 2, or 3. A simple route is just a route which cannot be written as a sum of two positive routes. So we have Jenkins diagrams with simple route edge, AN, DN, is size and three X case. Jenkins diagram with 2H, BN, and CN, and F4. And the particular Jenkins diagram with 3 edges, G2. So, in this theorem, I give the Cartan decomposition of the Lie algebra. So, for any complex sample Lie algebra, whose dimension is different from 3, and any arbitrary route alpha, there exists a Cartan decomposition related to this route alpha as follows. We have G is P alpha plus K alpha for any route alpha of any type of Jenkins diagram. Also for any short route in the case of type G2 or Bn. In the other cases of type Cn and F4, we have a Cartan decomposition like this. The difference between the first one is that P hat 1 is just a subspace of P alpha. I will define P alpha, K alpha, and prove that that is a Cartan decomposition. So we can work with simple complex Lie algebra, or take the split real simple form, which is isomorphic to this Lie algebra. HR is the real Cartan subalgebra, and we have the root space is of dimension 1 on R. And R have the same property for G and H. So now I define the subspace P alpha and the subalgebra K alpha. So I take the Cartan integers defined like this. So geometrically on Odinkin diagram, the number of edges between two sample routes, alpha and beta, is equal to this product, which is take the this value 0, 1, 2, or 3. We know that there exist two non-negative integers, P and Q, satisfying this relation for the integer beta H alpha. And also we can find this M alpha, it represents the alpha chain of routes, all the routes of the form M alpha plus beta, where M is between these two integers. So we have M between P, 1P and Q. So now I decompose the system of routes, and every subset will give me a subspace or a subalgebra, and every subset have particular properties. So here we take alpha is fixed. We take alpha and minus alpha, and subject R prime and R second, and we take disjoint unions. What is R prime? R prime is just the set of routes such that alpha plus beta or alpha minus beta is a route. R second is just the route such that both alpha plus beta and alpha minus beta are not a route. It's easy to see, to remember that. Now I give another characterization for any long route. R second is just the orthogonal of alpha. So R second, beta is in second if and only if beta is orthogonal to alpha. This, it's true for any long route alpha. And R prime satisfy this alpha beta is the half of the longer of alpha. Now for a short route alpha, we can have a route of the form M alpha plus beta. The possibility for M was 1 are here. So I will decompose R prime in union disjoint union as follow. It's just take 0 correspond R1 correspond to M equal 1, equal R2 for M equal 2, and R prime 3 for M equal 3. I write here correctly. R prime 1 is M alpha beta is a route for M only plus or minus 1. R prime 2 only for M 1 or 2 or minus 1 minus 2. R prime 3 corresponds to M is equal to plus or minus 3. R prime 3 is correspond to 3 edges in the Dennking diagram. So it's correspond only to the case of type G2. R prime 2 corresponds to the case Cn, Bn, F4, and when the Dennking diagram has simple edges, then all the routes are long. So we have R prime is equal to R1 prime 1, and R prime 2 and R prime 3 are empty. So we decompose now. There is another property for short routes. The set R prime 1 can be decomposed as a disjoint union, like this. The first one with tilde, both alpha beta and alpha minus beta are root. The second one, R hat, either alpha plus beta or alpha minus beta is a root. So I have this decomposition. The first one is like this. We take this one, don't change, and we decompose A prime like here with A prime 1, A prime 2, A prime 3. So now I will see some property satisfied by this subset of R. So since if alpha if beta is a root, minus beta is also a root, and since the while group acts transitively on the set of a root, we obtain the following property for all this subsets. So for R second, R tilde 1, R hat 1, and R prime 2, R prime 3, and also alpha minus alpha, we have E alpha is equal to minus E alpha, and is also equal to A minus alpha. Also, for any element of the while group, we have this relation. What this relation implies? Here we can choose alpha positive. So alpha positive or negative, we have this relation. For this one, we can choose alpha simple, and we act the while group to find the other subset. Now, for an arbitrary alpha, we have G is just the root space decomposition. K alpha is just the curtain subalgebra, and all the direction or the line where beta is orthogonal to alpha, or beta is equal to plus or minus alpha. And P alpha is the other direction. So we have P1 corresponds to beta and R prime 1, and PE corresponds to the sum of direction where beta is in R prime E. And for P1, we have P1 height and P1 tilde. Okay. So, is the direct sum is clear that G is equal to K plus P alpha. We verify that K alpha is subalgebra, and P alpha, the bracket P alpha is equal to P alpha, and P alpha is included in K alpha. We have the same property for the case of a short route, when in the case Cn and F4 with P1 height and K height. So this the adjoint orbit of the Lie algebra generated by E alpha and E minus alpha, which is isomorphic to SL2, allowed to give some sufficient condition on a semigroup S infinitesimally generated to be equal to the while group. So now I recall some property of the least saturated cone associated to a semigroup S. So as above, we consider S. infinitesimally generated by a subset gamma. The lesser iterated of gamma is just this, the definition. That means is the large subset of the Lie algebra generated by gamma, such that the closure of the semigroup generated by this exponential is equal to the closure of S. We know that this Lie saturated is a convex cone. Now I will add some other property, in particular with this Cartan decomposition related to root alpha. So we know that the Lie saturated is equal to the Lie algebra if and only if the semigroup is equal to the group. The algebraic condition implies that the semigroup has no empty interior, and the H, which is the large vector subspace contained in the Lie saturated, which is a subalgebra, is included in the Lie saturated. So now we consider G is a direct sum K alpha plus P alpha. If we take a subset gamma satisfying the rank condition, let gamma equal to G, then gamma is not included in K alpha because K alpha is a Lie algebra. So the Lie saturated 2 is not included in K alpha. That means that the Lie saturated has a component non-null, non-zero in the space P alpha. Now here I give the results, all the results concerning this problem. So we take a Lie group as above. S, a semigroup infinitesimally generated by gamma, and we denote by G alpha the one parameter group generated by the two direction A alpha and A minus alpha. So this theorem says that if the semigroup contains the subgroup G alpha for an arbitrary alpha, then S generates the group if and only if the subset gamma generates the Lie algebra. That is for any long route when G is of any type. And the same result is true for any short route alpha in the type G2. So one of this one was proved by Luis San Martin and Ariana dos Santos. And for the short route alpha, in another paper, they show that we have the same result for any long route alpha in type AN and or CN, and for any short route alpha in the case of type G2. They use the flag manifold. Here, with this decomposition, we obtain the results for any route alpha, and in the particular case G2, because they present a nice property and a good symmetry. So we have the same property for G2 directly as for any long route alpha. Also, Luis San Martin and Ariane, they prove that in the case for a short route in the case of type CN, this condition is not sufficient. That means that there exists an example for semigroup with no empty interior and that contains a subgroup G alpha, but is not equal to G. So here, there is a condition necessary concerning the case for short route when we have S generate G or S is equal to G. So the condition is the age. We take the projection of the Lie saturate on P2 plus. What is that? We have P2 alpha is the space vector, vector space generated by the direction of beta, where the Cartan integer is equal to plus 2 or minus 2. Here plus signifies that we take the direction R of beta such that the 2 alpha plus beta is a road. That means that the Cartan integer is equal to -2. Okay, this in fact in the Lie saturated, which is a cone, we can obtain just not only the line. So here we need to obtain all the line in the Lie saturated. So we characterize this space P2. So there is P2 plus and P2 minus. And we do this for the case Pn, Cn, and F4. We obtain this property in the case of type Cn. There exists one unique long road beta, and the seat R prime 2 is just this. Plus minus beta and plus minus 2 alpha plus beta. And the R here, that means that this alpha plus beta is a root, and here that means that alpha plus beta is a root. R tilde is equal to this. So the dimension of P2 plus alpha is equal to 2. Sorry. In the case of F4, we obtain 3 long roads. So the dimension of this space is an abelian subalgebra. If we take plus, and or similarly for P2 minus. So for every n, for Cn, we have the dimension of this abelian subalgebra is equal to 2. For F4 is equal to 6, and for Bn is equal to 2n minus 1. And here there exists n minus 1 long root beta E, and we have the same form in every case. There is other property concerning here I speak about R1 tilde, but I don't speak about R1 height. I will do this after, but here I don't need other property. So we obtain this result for simple algebra of type Cn. The group with finite center. We have the condition that S contain a subgroup G alpha for a short root alpha. So we have the equivalence S is generate G if and only if gamma generates the Lie algebra, and S contain one parameter group in the direction E delta, where delta is in P2, or delta is in P1 tilde. So here I speak about P2. Here I give the property of P R2, R'2, and R'1. Here is if delta is in here in R'1, just add alpha is delta is of the form alpha plus beta. If we add alpha, we obtain an element here. So we will characterize just this abelian subalgebra. So the condition for Cn for every n is that the semigroup contains a subgroup G alpha and one parameter group where the direction E delta is n R'2, which is equivalent to be in R'1. So what is Cn is very particular and is very simple because the dimension of P2 plus is equal to 2. For F4, the dimension is 6. So the question is, here we need to have a plane in the Lie saturated. So the condition was to add a direction, and we obtained the result. But in the case of type F4 or Bn, the dimension is 6, and for B3, 4, and for Bn is 2n minus 1. The question is, does only one direction will be sufficient to have S equal as G? So I give some other property in these cases, Bn and F4, to give the answer to this question. The question is simple. Does this theorem still true for F4 and Bn? Or we must to add other direction? So I take a root alpha, short root alpha, and a root beta as before. There is two cases. 2 alpha plus beta is root. That means the Cartan integer is 1 minus 2. The other case is minus 2 alpha plus beta is a root. That means the Cartan root integer is 2. Here we consider this this vector space. We take the direction A beta, A alpha plus beta, A2 alpha plus beta. We know that if the line A beta is in the Lie saturated by the adjoint orbit of SL2 with alpha, we obtain this one and the other one. So this vector space is clearly an abelian algebra, and it is included in, if one is included in the Lie saturated, or the abelian subalgebra is included in the Lie saturated. Now beta can be an arbitrary root just in R2 prime. So now we use another set of routes that concern to take the route which is orthogonal to beta and the route which satisfy this. That means in R height for R prime 1 height. So in the other case, we take the same thing, just the sign change here. Here we have minus alpha, minus beta, minus 2 alpha. In this case, we take the same thing, but here we change the sign. So this space is an abelian algebra and is stable by the adjoint orbit by the Lie algebra SL alpha. They verify other properties. Clearly, we have work with beta or 2 alpha plus beta give the same result. So we have this equality. We can take beta positive or beta no, or its opposite. We have this set I noted R bar. We have the same thing for routes. So also we have the same property as for alpha. Now we take just take A beta. It's not sufficient. So I add to A beta all the direction that are orthogonal to beta. So I take here minus, and I get here an abelian subalgebra. And we have the same thing for G minus beta, and we take the complementary of G beta in the Lie algebra. So we have this result. A beta is an abelian subalgebra, stable with the adjoint orbit of SL alpha, and G is a direct sum of G beta and C beta. G beta is a subalgebra. We can prove that C beta is also a subalgebra, but here for this problem, we need just that G beta is a subalgebra. That means that gives a necessary condition for L de gamma, the Lie saturated of gamma. Since G de beta is Lie algebra, it can't be, the Lie saturated is not included in this subalgebra, so he has a component in the C beta. So we obtain the same theorem for B3, for B3, the dimension of P2 plus is 4. If we take one direction, we have to recuperate the other 3 directions. So the result is true for B3. If the group has a finite center, we have the same condition for as in Cn. Here we have the same condition. Just we add one parameter group in the direction of one root or delta, which is in R prime 2. So for 3, the proof for 3 is not complicated. After for 4, the B4 and F4, they have the same dimension for P2 alpha, which we call 2, 6. But there is a lot of difference. In B4, in Bn, all P all P8 is empty. But in F4, we have two components, P8 and P tilde. So this result is true for P4 and F4, and we have the same proof. You use just the A beta and gamma, the root in R bar beta, and here if we and in the R bar beta, I type all the gamma in R second, which was orthogonal to alpha. Now I want that gamma be also orthogonal to beta, and I add this seat. In Bn, this seat is empty, but in F4, no. So we have this result for Cn, in particular for C2. So C2 is equal to B2. Now we have the result for B3 and P4, the same. The proof used just this decomposition and the property of the seat here. And for F4 is more for F4 is more complicated because it's particular. B4 have is not difficult compared to F4, because F4 the Dynkin diagram for F4 admits two simple short routes and two simple long routes, and the multiple edge, it's in the center, so you have nice property on the left and on the right for F4. The same result can be proved directly for Bn. Just generalize this property and use the lemma here for Bn, which characterizes this space. We can also take recurrence for Bn. Just it's true for B3 and F4, the same proof for P4, and we generalize to Bn, and we have the same result for the case of type Bn and F4. So, conclusion, for any route alpha, long route alpha, just S contain the subgroup G alpha suffice. The same, we have the same result for G2. For Cn, we have add one direction in order to have this space in in order to have the projection of the less saturate in the edge of the less saturate. And this result is true for the remanence case. So we need just three direction, A alpha, A minus alpha, and A delta for an arbitrary delta here. So now I will speak about Subramanian group. Here and some application, I give a simple definition. What is a Subramanian Lie group? It's just a triple GDB. G is a real dimensional connected and simple connected Lie group. D is a right invariant oriented distribution of constant rank K, satisfying the Allmander condition. B is the right invariant symmetric positive definite bilinear form on T. To a Subramanian Lie group, we we associated with sub-Riemannian algebra GPB, where G is the algebra of n dimension, P is an oriented subspace, and B is a symmetric positive definite bilinear form. So I give the definition of sub-Riemannian Lie group and sub-Riemannian algebra. I prefer to not give the definition of sub-Riemannian manifold M, D, and G, and give the particular case where the manifold is a Lie group and the distribution are invariant. So there is to any Lie group we associate only algebra. Just take the tangent space. The space is the distribution at the element unity, and the symmetric positive definite bilinear form is just the restriction to the distribution at at E. The orientation of the distribution induces or an orientation on the space P. We have the converse. To a sub-Riemannian Lie group, we associate a sub-Riemannian. To sub-Riemannian Lie algebra, we can associate a sub-Riemannian Lie group. So now we by identification by the left invariant vector with the Lie algebra, any Hamiltonian H can be identified with a Faber quadratic function on the dual of G.
Sorry,
the dual of
Professor Rachida,
we
have 7 minutes more. Okay.
Okay. Thank you. Okay, I will. So we have the Poisson bracket. We define the associated Hamiltonian here with this Poisson bracket, and we get the Lie-Poisson adjoint equation. So here I want to propose one result concerning the geodesic equation for 4-dimensional subhomogeneous space with a not contact distribution. I choose this because to study the Lie-Poisson adjoint equation, we need the classification of this sub-Riemannian Lie algebra. This classification was done by Eli Falbel, Professor Claudio Gorodowski, and Strickart in 1996. So, using this for subsymmetric space and not subsymmetric space. So we obtain this result for any sub-Riemannian Lie group with a not contact right invariant distribution. We have this equivalent property. The space is subsymmetric. The system of adjoint equation is Liouville integrable. That admits 3 quadratic functionally independent force integral, and all the optimal control are elliptic. In the case not subsymmetric, we obtain just 2 quadratic force integral. In some case, depending of the algebraic coefficient, sometimes there exists a polynomial or a logarithmic force integral. Sometimes it does not exist, and the optimal control are not elliptic. Another just remark here is just a perspective concerning optimal control. Many results use the non-decomposition G K plus P, where K is the maximal compact. In this case, we have 2 possibilities. we have a symmetric Riemannian space, Shika, and the control problem consists to study sub-Riemannian problem of minimizing the energy on the horizontal curve given by this system. Here I have a left invariant system, G dot GV, where V is in P. The second case use the Killen form, which is which define a scalar product in K, and if K is with finite center, we can study this problem of control, of optimal control, where V is in K. The perspective here is to use the Cartan decomposition associated to K alpha. The problem is that K alpha is not compact, but P alpha admits a lot of and interesting property. We can also use the equation GK alpha to obtain an affine symmetric space, and used the work of Louis and Martin concerning this affine symmetric space. Thank you for your attention.
Thank you, Professor Rachida.
I hope it was clear.
So, are there any questions? We still have time for 2 or 3 questions. Professor Sammartin, please.
Thank you. Thank you for your talk, Rachida. My question is, you prove your results with the assumption that the semigroup is infinitesimally generated. So I was wondering how much this assumption is needed. Have you thought about it?
Yes, I always need it, because I always because at the end my gamma is 3 direction, because to find perhaps I don't need it after, but at the beginning, to find necessary and sufficient condition, I look for generator. So if we have for this result 3 direction, perhaps we can assume that S is not necessarily generated by a subset gamma, but it contains this 3 direction, like your result where you give an example for the compressing semigroup. In this example, you look for the invariant cone. I can do the same things, but I always use the direction, because if the semigroup S, it's not necessarily generated by gamma, but if it contains this 3 direction, it's okay. But I don't know how to formulate this, because I always work with the direction. So I take the minimum semigroup, just this 3 direction. That is sufficient.
Okay. So, well, another question is, you work with the split real forms of the complex groups, and maybe the results can, it's not a question, it's a comment. Maybe the
Yes,
results can be extended for.
yes, yes. I already extended to any form, in a real form, for any route, any longer route. The result is valid if we take only algebra, which is not necessarily the slipped real form, but so we have complex route, and so we have to see what happened. For any route alpha, it's okay. For short route alpha, there is some type to verify, and there is some complication. But if the AD is, if it is true for longer routes alpha, it will be also true for G2, I think, because we have the same structure. And we can generalize this to the other case for short route alpha. But I have a preference for any real form with alpha or long route. And the other case I don't is not writing, is not. I don't write it.
Okay. Just to remember that in the talk of 11:30 by Bruno, he will talk about this same problem, but for the quaternion simple group, and also just to recall. Okay, thank you, Rachida.
Thank you.
So, any more questions? So, if not, let us thank Professor Rachida again, please.
Thank you.